All right, let's get right into it. The AP Physics C E&M exam. It is, no joke, one of the toughest tests you can take. It's this intense sprint of calculus and deep physics concepts. But what if I told you that the real secret to crushing it isn't just knowing the physics, but about cracking the code of the exam itself? Just look at that number, 77 seconds. That's it. In the multiple choice section, you've got 35 questions and only 45 minutes to do them. So yeah, that's the average time you get to read the question, figure out the physics, pick your strategy, and get the right answer. It is absolutely relentless. So, the million-dollar question is, how do you not just survive that kind of pressure, but actually thrive in it? Well, it's not about moving faster, it's about thinking smarter. And that is exactly what we're going to break down right now. The strategy you need to master this beast of an exam.
Your journey starts right here with the AP reference sheet. Now, a lot of students see this thing as just a safety net, but that's the wrong way to look at it. Think of this as your toolkit. Every single equation on here is a specialized instrument, perfectly designed for a very specific job. I mean, take a look at Gauss's law. This looks super intimidating, right? But it is an unbelievably powerful tool. It's basically telling you that the electric flux pumping through a closed surface is tied directly to the charge you've trapped inside. For problems with the right kind of symmetry, this tool can get you the answer in seconds, while other methods would take you minutes. Knowing when to pull it out of the toolkit is everything.
And this, right here, just nails the core challenge. As the experts at Fiveable put it, this exam isn't some memory test. It's a performance. It's about applying physics principles, using the language of calculus, and you have to do it fast. That whole toolkit is pretty much useless if you don't know how to actually wield the tools. Okay, so let's put these tools to work, shall we? We're going to walk through a classic scenario that you are basically guaranteed to see on the exam, the natural response of an RL circuit. This is where all that theory hits the real world, or, at least the exam world. So here's our circuit before anything actually happens. For a really long time, that switch has been closed. The current source is just feeding the circuit, and the inductor, because it's been sitting there for a while, is acting like a simple piece of wire. A short circuit. Everything's stable, it's predictable. We call this the steady state. And flip. At time t equals 0, we throw that switch open. The current source is suddenly gone, disconnected from the circuit. And this is the moment where everything changes. That stable, steady state, it's over. And the circuit now has to deal with this sudden change all on its own. This is what we call the beginning of its natural response. Now, look what's left. The inductor isn't just a boring wire anymore. All that energy it had stored up in its magnetic field has to go somewhere, right? So it starts driving a current through the resistor, basically burning off that stored energy as heat. The inductor is literally fighting the change, trying to keep the current flowing just like it was before. And this beautiful curve is the result. The current doesn't just slam to a halt, it decays exponentially. This curve, described by the equation I equals I naught e to the minus t over tau, is the signature of a first-order natural response. It's the mathematical story of that inductor giving up its energy over time. So what decides how fast this all happens? Well, that's the job of this thing called the time constant, which we call tau. For this circuit, it's just L divided by R. You can think of it as a measure of the circuit's sluggishness. A bigger time constant means a slower decay. And you absolutely have to understand this concept to analyze these kinds of changes on the exam. That circuit problem actually shows us something really important. To solve it, you need more than just some algebra. You need a completely different way of thinking. Let's call it your superpower, calculus-based thinking. It's not about finding a single number, it's about describing the entire process of change. This slide just lays it all out. Algebra-based physics, that's like taking a snapshot. It asks, hey, what's the current at exactly 2 seconds? But calculus-based physics C, it wants the whole movie. It asks, can you give me the function that describes the current for all time after the switch is flipped? See the difference? All right, let's try another core concept and see how this way of thinking builds. This is a super common question you'll see on the exam, and it sounds pretty simple. How do you get the electric field if all you know is the electric potential? And the answer is a derivative. Specifically, E is the negative gradient of V. Here's a way to think about it. The electric field always points in the direction where the potential drops the fastest. It's like a ball rolling down the steepest part of a hill.
The exam tests this constantly. They'll give you a function for V and ask for E. It's a direct, pure test of your calculus-based thinking. Okay, so you've got the toolkit, you've got the right mindset, but how in the world do you use them with that 77-second clock just ticking away in your ear? This is where raw knowledge has to become a real applied strategy. Mastering the clock is a skill all on its own. Here's a game plan, adapted from Fiveable's guide, and it works. First, you bank time. The first 10 or 12 questions are usually more fundamental. You nail those, and you do it quickly. Then you invest that time you banked on the tougher, multi-step problems that usually show up in the middle. Finally, you focus whatever time is left on the hardest, most complex questions at the very end. It's a real strategy. And a huge part of that game plan is knowing when not to answer a question. Seriously, it is so much better to answer 30 questions correctly than to rush through all 35 and make a bunch of careless mistakes. If you see a problem that looks like an algebraic nightmare or some bizarre setup you've never seen, circle it and move on. The strategic skip is your best friend. And that brings us to the end game. The absolute highest level of mastery is when you stop thinking like a student who's taking a test and you start thinking like the person who wrote the test. They aren't just throwing random questions at you, they're building puzzles, and those puzzles are based on very predictable patterns. The trick is to learn these patterns. You will be asked about derivative and integral relationships. You will see questions about proportionality. You will need to use vector calculus for things like flux and force, and you absolutely will have to recognize the shape of a differential equation for a circuit. When you start seeing these patterns, you can solve them almost on instinct. And this quote from Fiveable just sums it all up perfectly, doesn't it? The test is designed to reward elegance and insight. A problem that looks like an absolute monster to solve with algebra often has a beautiful, simple solution if you just apply the right calculus concept. That's the deep understanding they're looking for. Which leaves us with this one last thought. As you're practicing, try to shift your thinking. Don't just ask yourself, what's the right formula for this? Instead, start asking, okay, I've got 3 different tools in my toolkit that could probably solve this. Which one is the fastest? Which one is the most elegant? When you start asking that question, you're not just solving problems anymore, you're mastering the exam.